Hey everyone. So after walking you through this idea of basically just specifying a link function that helps us overcome this issue of out of bounds predictions with a linear probability model, we will now just quickly go through an alternative conceptualization of the logit and probit model, which focuses on basically modeling an underlying latent variable. An underlying latent variable that is ultimately determining the choice or the outcome that we observe, which is 0 or 1. But you can think of there being some unmeasurable component that ultimately leads to this observation of a 1 or an observation of a 0 that we can't measure, but we can still model it and basically relate it to the predictors that are included in our model. Okay, and so the most straightforward kind of way to think about this is to use or to think about like an underlying utility that someone derives from engaging in a certain action, right? Voting for a certain party or something like that, right? Obviously, we cannot observe people's underlying utility to do certain things, or we cannot observe, a politician's utility in voting for a bill or against the bill or something like that, right? But we can still kind of, at least conceptually, think about modeling this underlying unobserved utility and then think about different ways of relating this modeled underlying unobserved utility to our observed outcome, which is just this discrete 0 or 1 variable of voting for a bill or voting against a bill or voting for a candidate or and so on. Okay. Um, so in order to specify this latent variable approach, we kind of go through the same steps of specifying and defining a model as always by thinking about the underlying stochastic and systematic components. Okay, and first off, we start with our outcome, which is here we call it y star, but y star is now a continuous unobserved variable, right? You could think of this as utility, or if we were supposed to measure turnout, some kind of underlying propensity to vote, or health, or other underlying unobserved constructs that ultimately determine the observed outcome that is dichotomous. Okay, and so based on this kind of setup where we have such a continuous unobserved y star, this latent variable, we can specify our stochastic and systematic components as follows, right? Yn star first follows some probability distribution, yn star conditional on mu n, so the conditional on some expectation, and there's some probability around that expectation. Okay, and of course our systematic component is modeling that expectation. Okay, so the expectation mu n of our unobserved latent variable is modeled as a linear combination of our predictors and the coefficients, so beta prime xn. Okay. And then, as we said, yn star or y star is not observed in itself, right? We cannot measure someone's utility in any meaningful way, but we can observe the outcomes that are related to that underlying latent variable, right? And in our case, this is what we call then yn, which is just equal to 1 for all observations where this latent measure is larger than a certain threshold, which we call tau here, and is equal to 0 for any yn star that is smaller than this threshold tau. Okay, right? So it's still the same kind of setup. We have a dichotomous outcome that we observe. Okay, and that outcome, the data generating process, is that this dichotomous outcome, that is 1 or 0, is ultimately determined by this underlying continuous latent variable. And if that underlying unobserved latent variable is larger than tau, then we observe a 1. If our utility is high enough, then we turn out to vote. And if it's smaller than that threshold tau, then the observed outcome, the realized outcome that we see is a 0, right? But instead of directly measuring our observed outcome or directly modeling our observed outcome, what we do is we model our mu n, which is basically the expectation of our continuous latent variable. Okay. Okay. So given that y star is unobserved, right? We can't measure it. It doesn't really. It's just, you know, a latent measure that is kind of implicit in our model. That means that essentially this tau, this threshold, is basically arbitrary, right? We could set it equal to 0, or we could set it equal to, you know, some other measure, right? Because essentially we could kind of think of changing the scaling of our unobserved latent variable, right? You could think of this as, you know, it's similar to think of the underlying latent variable to be like a measure of temperature, right? It doesn't really matter. We could kind of think about this temperature being measured in Fahrenheit, or we could think about this measure, this latent construct being measured in Celsius or something like that, right? Obviously different 0 points, obviously different scaling, right? But you know, ultimately what we're describing is the temperature, right? So given that it's arbitrary, we can just, you know, choose a threshold that makes things easier for us, and so we just assume. Also to make this model ultimately identified, we just assume that this threshold is equal to 0, right? So as soon as our latent variable is positive, that means the observed outcome is 1, and when this latent variable is negative, then our observed outcome is 0, okay? That's just a simplifying assumption. We could use any other thresholds, but we have to make some choice with regard to the threshold in order to actually identify this model. We're also assuming independent realizations, so no autocorrelation, no interference between observations, and so on. Okay. So given this setup with this latent variable, we're modeling this utility, right? One thing that I kind of skipped over that we still have to decide is what is the underlying probability distribution for our unobserved latent variable, right? What is this P? What is this probability distribution? And ultimately what we have to do is we have to choose a distribution for P. Given that it is unobserved, we have to make some assumptions about that probability distribution, okay? So first what we can say is that we can, of course, we have a latent regression model. We have our yn star, which is equal to beta prime xn plus epsilon. So that's just based on the fact that our systematic component is just beta prime xn, and then we have an error term, and that ultimately determines our latent outcome yn star, okay? And we can assume, similar to the basic linear regression framework, or equivalent to the basic linear regression framework, we can assume that this epsilon, this error term, has a mean of 0 and a fixed homoscedastic variance, okay? And basically, since, again, this latent variable is unobserved, we can make an assumption about this variance and the size of this variance, right? And essentially what this variance comes down to, or what it comes down to, is that based on our assumption about kind of the shape of that probability distribution and the variance in this error term, we end up with either a logit model or a probit model, okay? So basically, if we set this variance equal to pi squared divided by 3, then this is equivalent to the standard logistic distribution, because the standard logistic distribution has a variance of pi square divided by 3, as we mentioned in the previous video. and if we assume the variance to be equal to 1, we assume a standard normal distribution. Sorry, I should have said the other way around. If we assume a standard normal distribution, then this error term has a variance of 1. If we assume a standard logistic distribution for p, then the variance in the error term is equal to pi squared divided by 3. Okay, so depending on what distribution we assume here, we get different error variances in our unobserved latent construct. Okay, and we could kind of, maybe we'll talk about in the Q&A session next week about this a little bit more detail. But this is similar to the previous video where we talked about logit and probit as different link functions that ultimately result in the same, or serve the same purpose in the sense of mapping our systematic component to a probability. This is again just an assumption about the underlying unobserved construct that we need to make in order for the model to be identified, right? And depending on what assumption we're making, we end up with a logit or a probit model, but the underlying quantities of interest and the substantive conclusion that are based on the model will again be the same, right? Because y star is ultimately unobserved, because it's a latent construct that we can't directly measure, similar to this tau being equal to 0, we just have to make certain identifying assumptions, right? And then based on those assumptions, we get certain coefficients. But again, the underlying probabilities that we're measuring, that we're estimating, and the underlying or the resulting substantive conclusions, they're still going to be the same. We just have to make different identifying assumptions. They result in different coefficients, but the substantive conclusions with regard to quantities of interest, they're still the same. Okay. So if we make these assumptions, basically, given the model's assumptions that we have made regarding the systematic component, the stochastic component, and this observation mechanism, and this distribution for our unobserved latent variable, we can then compute the probability of, compute the probability of observing y being equal to 1 based on this latent construct, right? And as we said, the threshold that we chose as an identifying assumption is tau being equal to 0. So the probability of observing a 1 is therefore equal to the probability of our latent variable being larger than 0, which, plugging in the systematic component and our epsilon is equal to the probability of beta prime xn plus epsilon being larger than 0, okay? Which we can basically flip around and write as 1 minus the probability of epsilon being smaller than minus beta prime xn, okay? We can further then specify this as, since epsilon has a mean of 0, we can basically write this as the cumulative distribution function 1 minus f of minus beta prime xn, okay? So essentially we can write yn, the probability of yn being equal to 1, as 1 minus the cumulative distribution function at the point minus beta prime xn, okay? And it turns out that if this cumulative distribution function f is symmetric about 0, which is the case for the logistic and the normal distribution, we can further simplify this 1 minus f of minus beta prime xn as simply f of beta prime xn. Okay, so essentially we can just evaluate the cumulative distribution at the point beta prime xn of this underlying latent variable in order to compute the probability of y being equal to 1. Okay, and now basically, and this holds for any type of probability distribution that we choose here for the underlying p for this latent construct, right? So now if we choose for F a cumulative standard logistic distribution, then this probability yields our logit model, which you should recognize from the derivation based on the logit link function. Okay. And if we choose a cumulative standard normal distribution for our F, then this ultimately yields a probit model. Okay, so I went through these kind of fairly quickly. The point is here that we can basically, just by thinking about modeling this probability based on an underlying latent construct, and then making certain identifying assumptions about the distribution of this underlying latent construct, of this underlying latent variable, we can again kind of compute the probabilities of observing a 1, conditional on x, conditional on our x's and our betas, and depending on what kind of assumptions we make about this underlying latent construct, we again end up with the logit model and the probit model the same way we ended up with those two models, by just going through the logic of specifying a link function in our first kind of conceptualization of both models. Okay. We will probably take a little bit more time in the Q&A session to kind of go through the logic behind this and the underlying reasoning. And I hope with some of the coding examples and some of the examples that we're going to go through, that will become a little bit more clear as well. Okay. What you should, of course, remember for now is that at least for your substantive questions, whether or not you're using logit or probit, shouldn't really make a difference. It will ultimately give you the same substantive results, right? The coefficients look different, but the underlying probabilities that you're modeling, the underlying quantities of interest, they will still be the same. When we're using STAN, in most cases, we will just use the logit model. In STAN, the logit model is slightly more stable, and it also is computationally a little bit faster, so that's one advantage for the logit, at least in STAN. If you're using classic like the basic frequentist base R functions for logit and probit, it doesn't really make that big of a difference. So you can basically go back and forth from one through to the other. And as I will show you in the next video, there's also a correspondence, as we mentioned, where we can basically convert a logit model coefficient into an approximate probit model coefficient as well. Okay. All right, so much about logit and probits. I hope this kind of background information that is not directly kind of included in the textbook will help you kind of contextualize some of that information in the readings. And in the next video, I'm going to go through a quick coding example that was also discussed in the textbook, and I'm going to just go through some of the commands to actually estimate logit and probit, or logit models for now, in R using STAN. Okay, so that'll be the next video, and so I'll see you in a second.